Thanks for coming to this Jones Seminars talk today. And we have the pleasure of having Professor Amedeo Odoni of MIT as our Jones Seminar speaker today. So let me say a couple of things about him and then we can get started. So Professor Amedeo Odoni is the T. Wilson Chair Professor Emeritus of Aeronautics and Astronautics and of Civil and Environmental Engineering at MIT. He specializes in operations research and its applications to transportation systems and to urban services. Among many positions, he has served as co-director of the Federal Aviation Administration's National Center of Excellence in Aviation Operations Research from 1996 to 2002 and of MIT's Operations Research Center from 1986 to 91. He has more than 100 professional publications and 9 books to his credit, including the popular textbooks Urban Operations Research with Professor Larson, Airport Systems with Professor D. Neufville, and The Global Airline Industry, co-edited with Peter Bello-Baba and Sidney Barnhart. He is a member of the National Academy of Engineering, a fellow of Informs, and the recipient of many, many awards for his teaching and research. He has also served as consultant to many of the busiest airports in the world on projects related to planning and design and to air traffic management. And today, he's going to spend some time talking about some of his experiences over the years. So please join me in welcoming Professor Odoni here.
Thank you very much, Professor Weise. It is a great pleasure for me to be here. And things look already familiar because when we are in a big room at MIT, everybody sits as far back from the speaker as possible. So again, it's a pleasure for me to be here, and thank you very much for being here on a Friday afternoon. What I would like to do is talk about the airport capacity crunch, as I call it here. I did my PhD thesis at MIT in 1969, and it was on airport capacity and airport delays. And at that time, there were exactly 3 airports in the whole world. LaGuardia Airport in New York, JFK Airport in New York, and London Heathrow. These were the only 3 airports in the world that were experiencing any kind of air traffic delays. And things have gone downhill ever since. Today, there are literally hundreds of airports around the world which are experiencing very serious congestion problems. And in addition, the system has become so interconnected through many flights and so on that if there is a disruption or a major delay in one important airport, these delays quickly propagate throughout the system, throughout a nation, or even throughout a continent. So this is essentially what I would like to address here. And my plan is to concentrate on the airside capacity. As many of you know, from bitter experience, I assume, terminals are very crowded, passenger terminals. Queues for security are very long, but I believe these are temporary types of problems. The long-term problem in airports and in air transportation is that the capacity of the airside, the runway systems, the taxiways, the aprons, cannot keep up with the demand as the number of flights is increasing and so on. So I would like, as I said, to focus on airspace capacity. I'm going to say a few things as background and describe quickly current conditions. And then I'm going to talk about the capacity of runway systems, single runways, multiple runways, and the effects of weather on the capacity. And then at the end, I'm going to talk about how three different regions in the world, the three most important regions, Asia, Europe, and the United States, are addressing or not addressing the airport capacity problem. And this, as you will see, will be a general purpose talk. There will be few equations, if any, and so on. So, to begin, some general background. First of all, air transportation throughout the world is truly booming right now. It is at the top of anywhere it has been in its history. So, in terms of passengers, we had in 2016 all-time highs in the number of passengers in practically every region of the world. In 2016, 7.4 billion people went through airports, either arriving or departing through airports. In 2017, which is a great year again for air transportation, the number of airport passengers for the first time ever is going to exceed the world's population. It's going to be about 8 billion people going through airports. And when it comes to commercial flights, again, we have all-time records everywhere except for the United States. In the peak year in the United States for air traffic for commercial services was in 2007. After that, there was the financial crisis, and as a result, the number of flights went down, of scheduled flights, and they have begun picking up again since 2013, 2014. So today, we have 13% fewer flights in commercial flights in the United States than in 2016, but at the 30 busiest airports, which are really the key to the whole thing, it is only 5% less, and it is expected that perhaps in 2018 we'll go back above the 2007 mark. So this is one thing to be aware of, that we are in a boom period. The second one, which very few people realize, is that we have very high concentration in the airport sector. As you can see here, the 30 busiest commercial airports in the world, out of a total of 4,000, just 30, handle about 26% of all enplanements, and the top 100, about 58%, again, 100 airports out of 4,000. So we have a small number of critical airports that, if they get congested, they create tremendous problems throughout the system. And the United States, the 30 busiest out of the 500 or so airports that provide commercial service, account for 64% of all enplanements. So again, a very highly concentrated sector. So that means that these major airports are extremely important to the functioning of the air transport system. Now, many of these airports are currently operating at or near their capacity limits. Many are operating in what I call, you'll see in a second, the red zone of utilization, and outside the United States, not in the United States, we see increase in use of slot coordination. I'm going to explain in a second what these mean. First, about the red zone of utilization. Runways, airfields, are essentially queuing systems. They provide the service, and airplanes queue up to land and depart at these facilities. Now, queuing systems are well known for the very non-linear relationship that exists between, on the one hand, expected waiting time, and on the other hand, utilization. What do we mean by utilization? we mean the ratio, the utilization ratio is the demand rate, how many movements are requested per unit of time, divided by the service rate. How many can we serve per unit of time? People call it simply demand divided by capacity. That's the utilization ratio. And as you can see in this picture, there is a point here at which this relationship between expected waiting time and the utilization ratio turns dramatically up, because the relationship says that this relationship is dominated by this 1/1 minus rho. So when the utilization ratio approaches 1, in other words, when the demand gets equal to close to capacity, the delays begin becoming increasing very, very quickly. And it so happens that all these major airports that we are talking about are operating in this zone here. This thing here is depending on the airport, on the number of runways and so on. This is something like 0.8 or 0.85. In other words, when the demand gets to close to 80% or 85% of the capacity, all of a sudden the delays become very unstable. A small change in the demand may mean a big increase in the delays, or a small reduction in the capacity may also mean a big increase in delays. As a historical curiosity, you see this is 4 minutes of expected delay. When I was doing my PhD thesis in 1969, the FAA had a rule that said when the average delay in a peak hour at an airport for landing or for takeoff reaches 4 minutes, the airport should be considered to have reached its practical capacity, okay? 4 minutes. Today, if you can land or take off in 4 minutes, you applaud the pilot. You say, oh, great, this is fantastic, okay? So that was back 50 years ago. Now, most airports operate with delays of 10 minutes, 15 minutes, and that kind of thing. At London Heathrow, when they prepare their schedules for the next season, they schedule a number of movements such that the average delay for the entire season, average delay not in the peak hour, over the entire season for an airplane landing is 10 minutes at London Heathrow, and the average delay for departure is also 10 minutes. So when you schedule a flight to London Heathrow, essentially you're signing up for an expected value of 20 minutes of delay, which for a 747 or Airbus 380, that means a tremendous cost to the airline. So keep that in mind, that we now have a large population of airports operating in the red zone. Now, the second item here, the slot coordination, is something which is not really recognized in the United States. We call slot coordinated airports level 3 airports. This is international terminology for the level of congestion at an airport. And in the United States, we have just one airport, which is level 3. It is JFK International in New York, okay? But in the rest of the world, there are something like 180 the most important airports outside the United States. The great majority of those are level 3. And what does that mean? It means that the airport specifies an upper limit on how many flights can be scheduled per hour at that airport. For example, as given here, will accept 72 movements, landings or takeoffs at this airport. Then the airlines submit requests for these slots the requests are for 5-minute slots. So 16:05, 16:10, 16:20, and so on. You can have multiple assignments given in any 5-minute slot. And then there is what you call the airport slot coordinator, who allocates those slots to the airlines requesting them. So essentially, this is back to a pre-deregulation period. In other words, we have the slot coordinator acting essentially as the regulator of who gets access to the airport and who does not get access. And worse than that, there is something called the grandfather slot, the grandfather clause, or what we call historical rights. And that means that if an airline used a slot in the previous summer, it is automatically entitled to the same slot in the next summer, and then in the next summer, and so on, okay? Which means that we have the phenomenon of what we call fortress airports, meaning if you go to Frankfurt, for example, Lufthansa has 70% of the slots. And it's essentially a monopoly market in Frankfurt. Similarly, at London Heathrow and that kind of thing. So this slot coordination business is essentially a propagation of the old days of a regulated industry by controlling access to the airport. So keep in mind, this is something which is not done in the United States because it's national policy not to avoid as much as possible slot coordination, but everywhere else in the world, this is now becoming a common phenomenon. And to continue with that, you can see immediately the consequences of this can be very important. Inhibits the growth of traffic, greatly reduces the level of service, long air traffic delays, but increasing the capacity of these airports is a very difficult and time-consuming business. And I have here a slide based on a study that I participated in for the FAA. I believe Professor Vazir was also involved in that. And you can see here the cost of delays, air traffic delays in the United States in 2007 was estimated as $32.3 billion as direct costs plus some indirect costs and so on. This is 2007 because, as I mentioned, that was the worst year in the history of the United States in terms of air traffic congestion. And we are getting back now to these levels. We are talking about enormous amounts of money. So let's talk now about the capacity of runways and of runway systems. First, the runway itself is the bottleneck of the system. I hope you recognize why. We have a three-dimensional space where airplanes fly, and eventually these three dimensions have to be squeezed into a single dimension, the runway, so everybody is brought together and they fly. As you can see, they reach what is called the approach gate here, and then they fly this final approach path, which has an angle of about 3 degrees with the horizontal. It's about 5 to 7 miles long, depending on the airport, and then they land on the runway. And as indicated here, runways are the component of the airport which is most resistant to expansion. I need not go through the details. You all know how long it takes to ever receive an approval for a new runway. London has been struggling with these problems since 1965. They have been trying to add one runway to the London airport system. There are 5 airports in London. They want to add 1 more runway, and they are still fighting about it. The government has now promised a decision for next year, and it may take another 15 years before they build it because of legal issues and things like that. So most resistant to expansion. A somewhat technical point. How do we define runway capacity, and how do we define airfield capacity in general? As you can see, we use now words from probability theory. It says the expected number, the average number of runway operations that can be performed in 1 hour without violating air traffic management rules, assuming continuous aircraft demand. So the idea is, suppose you have a huge queue of airplanes circling, waiting to land on a runway. Suppose this table is a runway. How many airplanes can we push through this system per hour? This is what we call the maximum throughput. What is the maximum throughput we can achieve for an airport? It's also called the saturation capacity. So the point to remember is that capacity is not a deterministic quantity. It is essentially a probabilistic quantity. The number of movements per hour that you can do is a random variable. And the capacity is defined as the expected value of the number of movements that you can perform. Why is it probabilistic? Because the capacity, the number of movements you can do, depends on many factors. And I have here listed the most important ones: the number and layout of active runways, separation requirements, weather, and so on, mix of aircraft, etc. I'm going to talk about only the ones which are in red here. The others are more or less obvious. Just to explain, for example, this mix of aircraft means whether the airplanes which are landing are heavy airplanes, meaning wide-body airplanes, or narrow-body airplanes, or small airplanes. That plays a major role in determining the capacity. But as I said, I'm going to concentrate on the first 3. And specifically, I'm going to talk first about the capacity of a single runway. This is a picture of London Heathrow, London Gatwick Airport. This is an airport that has a single runway, but it's used so intensively that it has about 30% more passengers, processes 30% more passengers than Boston Logan Airport, which has 6 runways. We have this single runway, and it is used from the morning at 6 o'clock until 11 at night, intensively with its full capacity, so they get about 40 million passengers a year out of this single runway. Now, how do we determine the capacity of this runway? Well, the first thing we have to do is to look at the separation requirements. We have air traffic control separation requirements designed to keep the airplanes safely separated from each other. So, as you can see, typically airplanes are separated into different categories depending on their maximum takeoff weight. Essentially, the maximum takeoff weight is used as a substitute for the size of the airplane. And we have in the United States 5 classes of airplanes for purposes of air traffic control. Super heavy, which is just the Airbus 380, heavy, which are wide-body airplanes. The Boeing 757 is a special category because it generates very strong wake vortices, and this airplane is not in production anymore, so this class is going to disappear in the future. And then we have large, which is the large majority of airplanes, of commercial airplanes, the Boeing 737, the Airbus 320, all these medium-sized airplanes, narrow-body, single-aisle, these are all large airplanes. And finally, we have the small airplanes. And these rules specify for every pair of this type how many miles of separations are needed on arrival and how many seconds of separation are needed on departure. Incidentally, this is not the only classification, and this causes all kinds of problems around the world. ICAO, the International Civil Aviation Organization, which is essentially the United Nations of air traffic control and of air transportation, has its own classification. United Kingdom has its own classification. The French have their own classification, so different countries use somewhat different classifications of airplanes. But let me show you the picture here. This is for the United States under instrument flight rules. When airplanes are flying by instrument, on the same runway, if we have arrival followed by arrival, we have the separations that you see here. Just to take an example, suppose, for example, I have a super heavy, this is the leading aircraft, super heavy, followed by a heavy, that this table says 6 nautical miles. A nautical mile is 1.15 statute miles, or 1,852 meters, something like that. We require 6 nautical miles separation throughout the final approach. As these airplanes approach the runway one after the other, they have to be separated by 6 nautical miles. So you see the separations, if you have a super heavy followed by a small airplane, they require 8 nautical miles, about 15 kilometers for those of you who like to think about in kilometer terms. That's a huge distance between 2 airplanes. And these are 2 consecutive airplanes landing on the runway. Now, you see all the numbers indicated in red here are numbers caused by what we call the wake vortex effect. Airplanes, as they fly, generate through their wingtips wake vortices. And if an airplane is following too close to the previous one, then it may be susceptible to accidents and so on if it is caught in that wake vortex. So as you can see, when you have a big airplane, SH or H or even Boeing 757, followed by a smaller airplane, we have wake vortex separations. If you do not have wake vortex separations, then the separation requirements in the United States are 2.5 nautical miles. So when they are landing on the runway, they must be separated by these distances as they approach. And as you can see in number 2, it says the leading airplane must be out of the runway before the next airplane touches down, again, for safety purposes. Both of these things have to be satisfied. And I'm not going to spend any time on this, but there are similar separations for departure followed by departure, departure followed by arrival, arrival followed by departure, and so on. Incidentally, my slides will become available to you, so those of you who want to take a closer look are most welcome to. And similarly, I have here the ICAO separations, the ICAO recommended separations. These are the more international separations. If you look closely at this, they are very similar to the FAA's, they are a bit more conservative than those of the FAA. And individual countries have the right to impose more restrictive separations if they so wish. So, for example, China, which now has maybe the worst congestion problem in the world in terms of air traffic congestion, has adopted some very conservative separation requirements to ensure absolute safety and so on, but this is reflected, as I said, in huge congestion and in low capacities at Chinese airports in terms of processing aircraft. Now, once we know these separation requirements, what we can do is compute the capacity of the airport by doing the following thing. You see, this is the matrix Tij. This is the minimum time required between the arrival of a type I airplane followed by the arrival of a type J airplane. So, for example, this number here indicates that if we have a heavy followed by a heavy, if they follow the rules, on average, it takes about 113 seconds between the successive touchdowns of these consecutive airplanes. If you have a heavy followed by a small, you see it's almost 4 minutes. But if the small is followed by heavy, it's a 74 minutes. 4 minutes and 74 seconds, okay? So these separations is 3 times that, right? And as I said, this is the matrix of average separations. By the way, there is no SH here because SH are very, very unusual. The Airbus 380 has very few flights in the United States, and as some of you may be aware, the Airbus 380 is considered to be a failed airplane in the sense that the airlines are not buying that airplane, so production may actually stop in a few years. So we have this matrix of separations, and and it's the same thing that you see here. And I give an example. Suppose that the aircraft mix is 15% of the airplanes are heavy, 75% are large, and 10% are small. And at airports at this time, most of the airports use first-come, first-served discipline to land at airplanes. In other words, the first airplane that shows up in the terminal area is number 1 in line, the second one is number 2, and so on. So assuming first come, first served, the probability of having a heavy followed by a heavy is what? 0.15 multiplied by 0.15, or about 2.25%, or 0.025. PHL is 0.15 multiplied by 0.75, and of course PLH is also the same thing. So for each one of these 9 numbers, we can compute the frequency with which these numbers will show up. And all I have to do is multiply 0.00225 by 113, 0.1125 by 181, and so on, each number here by its corresponding frequency, and I come up with a number which is the expected value of t, 102.5 seconds for this particular matrix here, and for this particular case, particular mix. What is this 102.5? It is the average interval over a long time, if I observe the runway over a long time, between successive landings of airplanes. So the capacity now is simply 3,600 seconds in an hour divided by 102.5, and that comes to about 35 arrivals per hour, which is a typical number that you see in the United States. So the computation of capacity is actually an easy thing to do if you know the rules and if you know the approach speeds of the airplanes, the length of the final approach, and that kind of thing, right? So this is one point to remember, that it is quite easy to compute the capacity by computing based on the separation requirements. Now, the next thing to notice is that it is natural to think about improving things by getting away from first come, first served. Okay? Suppose I have an S, a small airplane, and a heavy airplane, an H. If H is in front of S, I need 4 minutes to land them, 226 seconds. If the S is in front of H, I need only 74 seconds. So it is natural to say, okay, when we have a choice, we put the S in front of the H. Is it always like this? Certainly not. I mean, if you think about it, the heavy airplane may have 400 passengers. The small airplane may have 30 passengers. So by putting the S in front of the H, you are essentially giving priority to the small number of passengers over the large number of passengers. So the point is that there is this arrival sequencing problem, which is a problem that has attracted many PhD theses, some very recent ones, that deal with operating in an optimal way the runway by sequencing airplanes properly. And I give here a reference to this particular paper, which is an excellent paper that summarizes this whole area. I'm going to skip a couple of technical slides and go now to the multiple runway situation. We spoke about the single runway. We said the requirements, the separation requirements drive the capacity of these runways. Now, when you have more than one runway, things get more complicated because the runways may be sufficiently close to one another that they interact with each other. And we have some common geometric layouts at airports that have different requirements each for the separations. And primarily we have many cases at airports where we have parallel runways. And as you can see, you can have close-spaced parallels, medium-spaced parallels, and independent parallels depending on the distance between the center lines of the parallel runways. Okay? And then we can have intersecting runways and converging, diverging runways. So let me show you a few examples. This is Dusseldorf International Airport. It has two closely spaced parallel runways. 494 meters is the distance between this and this. You see if the separation is between 365 and 760, these are considered to be close parallel runways. What does this mean? It means that the two runways, when they are run by air traffic control, have to be coordinated. And by that we mean that what happens on one runway affects what happens on the other runway. At this airport, and in general, this runway here will be used for departures and this runway for arrivals. And what happens is you have suppose you have an arriving airplane, it's coming in to land, and the departing airplane is waiting here on the runway to take off, and the departing airplane is not allowed to begin its takeoff until the arriving airplane is safely down on the runway. Okay? So essentially, the capacity of this system is twice the capacity or the arriving capacity of a single runway. You see the point? Again, we have one runway for arrivals, the other runway for departures, and they must be coordinated and synchronized so that you do not have any violations of safety issues. Now, the next example is from Malpensa Airport in Milan. I have done a lot of work there. And this is an example of medium-spaced parallel runways. As you can see, the separation is 805 meters, so between 760 and 1,525. The rule for these runways, when they are medium spaced, is that operations on one runway can take place independently of operations on the other runway, except for the case when you have arrivals on both runways. Simultaneous arrivals on both runways are not allowed. The distance, they are considered to be, the runways are considered to be too close to one another to allow for two airplanes to come in parallel and land in this under instrument flight rules. And then the third case is independent parallels. This is now Munich Airport. You see the separation between the runways is 2,296 meters, which is more than 1,525 meters. What that means is that the top runway here is operated independently of the bottom runway. It's like having two different airports, each with one runway each. So you can see that as the distances between runways increase, that means that the capacity of the airport goes up because there are fewer dependencies between operations on the two runways. And again, if you increase the separations, you sacrifice in terms of land area, so there is always a trade-off between land area on the one hand and capacity of the airport on the other. You see, by the way, I mean, just this is an interesting aside, you see this runway has what we call an offset from this runway, okay? And suppose you have operations in this direction. Then, in this configuration, the top runway there will be used for arrivals, and the bottom runway will be used for departures because that minimizes the taxiing times that airplanes are going to experience. What I mean is you have an arriving airplane, and then it takes an exit here, an exit there, and goes directly to the apron areas of the airport. And similarly, in taking off, they go here, so they taxi for a smaller distance than otherwise with this configuration. This particular layout, two independent parallel runways with the terminal buildings in between, is becoming almost a standard design for airports around the world. The next one is, you see, Gwangju Airport in China. Same idea, two independent parallel runways. Practically all the new major airports that have been constructed in the world in the last 20 years have this kind of configuration. And the next table here summarizes all the rules. I'm not going to go over that, but you see, again, when you have independent runways, we have independent, no matter whether they are used for arrivals on one runway and arrivals on the other, or arrivals and departures, and so on. And notice that the FAA, instead of requiring 1,525 meters, also allows 1,310 meters, or 4,300 feet. UK also, and a few other countries. So the FAA has reduced the required separation between parallel runways from 1,525 to 1,310 meters for independent operations. How does this help? It helps because some airports may not have runways separated by 1,525 meters, but by 1,400 meters. For example, this is London Heathrow Airport. You cannot see it very well on this picture. Two parallel runways here. they are separated by 1,390 meters. So the UK reduced the requirement to 1,310 meters and declared that the two runways are independent. And this kind of game is being played sometimes. And then we go to, what we call mega airports. This is Paris Charles de Gaulle, two pairs of close parallel runways, one at the top, the other at the bottom. So the capacity of this airport is essentially twice the capacity of Dusseldorf Airport that we saw before. These two runways are completely independent from these two runways at the top. So this is how it works. Atlanta, as many of you know, this is the busiest airport in the world. It exceeded 100 million passengers in 2015 for the first time. It had 105 million passengers in 2016. And you see we have two pairs of close parallel runways, independent close parallel runways. And in 2007, they opened a fifth runway down here to relieve those four runways. This is another beautiful picture of Atlanta. You see here the complex of terminal buildings there, which is considered extremely good for transfer operations, for connections of passengers, and so on. Again, we cannot go into details. And then we have the case of intersecting runways, LaGuardia Airport. Notice here, there has to be full coordination between the two runways. If you have, for example, arrivals on this runway and departures from this, the departures must wait until the arrival is completed. Either the airplane is out of the runway or it crosses the intersection before you can release the departing airplane. So for intersecting runways, you need close coordination. And then there is Istanbul Airport here. You see there is a pair of runways here and another runway here. Notice what happens here. If you operate the airport in this direction, if the wind is from the north, then they land on this runway and they take off on this runway, everything is fine. It's like having two independent runways. But if the wind is from the south, then if you land here, you cannot take off until the landing is completed, and then you can have a takeoff. So again, depending on the configuration, it makes a huge difference as far as the capacity is concerned. I'll just show you Dallas-Fort Worth with 7 runways. This runway has not been built yet, but the other 7 have been built. 1, 2, 3, 4, 5, 6, 7. And this is the airport that has the highest capacity in the world in terms of aircraft movements. Another picture here shows how complicated this airport is. It's a maze. And I think in the process, I said a few things about the influence of weather. As I indicated here, weather plays a critical role, not only in respect to the capacity of a single runway, because when the weather is poor, they allow for longer separations, which means lower capacities, but also because the wind is important in determining what runways can be used, in determining what we call the configuration, the runway configuration to be used at the airports. So different configurations may have very different capacities, and weather is the major cause of uncertainty regarding availability of capacity. The capacity of an airport may change greatly depending on the weather conditions on any particular day. Logan Airport, which I assume most of you are familiar with, is a prime example of the importance of weather. We have 6 runways in 3 different directions, and depending on which way the wind is blowing, we may have tremendous variation in the capacity of that airport. In fact, this is shown in this picture here. Take a look at this and see how complicated issues this point raises. Just to explain, this axis here is the percent of time, so this goes up to 100%, and this axis shows how many movements per hour can be performed at Logan Airport in Boston. So as you see, for about 62% of the time, or whatever this number is, 62% of the time, Logan can handle something like 130 movements per hour. And that's under ideal weather conditions. But then there is another 15% of the time when the capacity goes down to 115 or so, and you see we go progressively. In fact, there is about 2% of the time here when Logan has 0 capacity. Why is that? Snowstorms, thunderstorms, and that kind of thing, okay? So what is the ideal? How many movements should be scheduled at Boston during peak hour? It's a very interesting question. It's like the half empty or half full glass, okay? What do we do in the United States? We take a very optimistic view. For example, at Logan, the typical peak hour demand is about 105 movements per hour, all right? What does that mean? That means that for about 22% of the time, Logan does not have enough capacity to handle the traffic, okay? That means 1 out of 5 times you go to Logan Airport. Many countries outside the United States take a much more conservative view, and they, for example, might set the limit here, which means that they are wasting huge amounts of capacity in order to achieve reliability in the service at the airport. So again, there are these trade-offs, and there are policy decisions that have to be made. I have a slide here that indicates the range of capacities at major commercial airports around the world. The thing to notice is that these numbers change greatly from country to country and from airport to airport, depending on separation rules used, the configuration of the runways, and so on. And for major airports, we have capacities ranging from 30 up to 260 per hour. This is Dallas-Fort Worth. So one of the things that is done today is to try to increase capacities by even marginal amounts so that to take advantage of this red zone utilization. I say at high levels of utilization, even small increases in the capacity of the runway system can have a large impact on reducing air traffic delays. And this is shown again in this picture, that if you are operating here and increase the capacity by 5%, you may go down here in terms of delays. A small increase in the capacity may mean a large reduction in delays. So much of the motivation behind some of the big projects that are taking place now in the world, the Next-Gen program in the United States, the Cesar program in Europe, several others. There is China has one, India has one, Brazil has one, to modernize the air traffic management system. They are not aiming for huge increases in capacity, only for marginal increases that may reduce, however, significantly the delays. And I say at the bottom, but there is only one silver bullet for really increasing the capacity, and this is to build new runways. And unfortunately, we are not in position in this country or in Europe politically to achieve that. So to finish my presentation, let me talk briefly about these regional differences. First of all, these three regions, Europe, USA, and Asia, dominate air transportation in the world. And notice here, this is 1999, 2008, 2016. The United States in 1999 had 19 of the 30 busiest airports in the world by number of passengers. This number is down to 10 now. And by contrast, Asia has gone from 5 in 1999 to 14 in 2016. And of course, in the future, we are going to see more and more Asian airports becoming the mega airports of the world. And Europe has been more or less constant over the years. Now, what is interesting is if you look at these three regions, they have three different sets of perspectives on airport capacity and three different sets of approaches or non-approaches. So as far as the United States is concerned, the first thing to note is that we have large capacities at our airports in this country. And the reason is that we have many runways at most of these airports. As you can see, about 4.1 runways per major airport in the top 30 airports in the United States. In Europe, it's 2.47 runways per airport in the top 30 airports. Practically no slot controls. We don't have slot coordination in this country with the exception of JFK Airport, as I mentioned. And we have capacities ranging up to 279 movements per hour under good weather conditions. VMC means visual meteorological conditions, good conditions. And IMC means instrument meteorological conditions. So we have many airports in this country which have a capacity of more than 100 movements. Amazing. In the rest of the world, there are only 3 airports right now, Charles de Gaulle in Paris, Amsterdam, and Madrid, that have a capacity of more than 100. But China, for example, is building 2 or 3 airports, mega airports, that will exceed that. And in Europe, we are going to see several, including Istanbul Airport, which is going to be the biggest airport in the world, and so on. So we have a lot of capacity, and what we can expect to see in this country is what I call here more of the same. And by that, I mean we are going to continue seeing a tight balance between capacity and demand, which is the case right now. And that means many airports will be in the red zone, but there is not much we can do about that other than improve the air traffic management system as much as we can, because very few new runways will be built in this country in the foreseeable future. So they will continue to operate in the red zone, and we are going to see, this is an interesting picture, a tremendous dependence on weather as far as delays are concerned. If you look at this, it says average delay relative to schedule of scheduled arrival time and scheduled arrival time at the 34 busiest airports in 2007, again, the worst year in the history of the United States as far as delays are concerned. This is for in visual weather, in good weather conditions. This is in poor weather. And see, and this is time of the day. So you can see that in bad weather conditions, the delays began in the morning and then they kept increasing during the day, meaning that the system could not keep up with the demand. So airplanes were falling behind schedule, And up here, you see the average delay, average at the 34 busiest airports in poor weather conditions, 32 minutes, okay? Amazing. Very, very bad delays. And of course, if you go to New York, you see much worse delays than that. So again, in the United States, more of the same, tight balance, may get back to record levels of delay if the demand continues to increase. Now, but in sharp contrast, if you go to Asia, you see a very different picture. What happened in Asia? This is Hong Kong Airport. It's all built on a landfill, enormous costs, I think 15 or 17 billion US dollars when it opened in 1998. You see two parallel runways, this runway and this runway over here. This is the cargo area, and this is the big, huge terminal building in Hong Kong. Now, this airport, when it was designed for 87 million passengers to be reached in 2030. I forgot to mention, the airport was opened in 1998, okay, just 20 years ago. It was designed to last with the two runways until 2030 or 2040, but next year is going to run out of capacity, okay, in just 20 years. And the reason is that they assumed that they were going to have 348 passengers per arrival or per departure. In other words, that all the airlines were going to be using big airplanes. The reason was that back then, in the 1990s, most flights to Asia were intercontinental flights that were using wide-body airplanes. And what happened after 2000 is that there was a lot of regional development. Airlines bought smaller airplanes, so all of a sudden the airports were flooded with flights. And the two runways they built for Hong Kong were inadequate to serve the traffic. So instead of having 348 passengers per movement, in 2016, they had 171, one half of what the forecasters had said. And because of that, instead of anticipating 87 million passengers in 2030, they now have 70 or 75 million passengers as the absolute limit of what Hong Kong can handle, because they have run out of runway capacity. And now they have a new program to build a new runway here, the third runway, by extending the airport into the sea, very deep waters there. It's a gigantic project, $17 billion just to build that new runway. If you go to Hong Kong and you are a civil engineer, your heart will palpitate. I mean, you'll see a runway coming out of the water as they do landfill and so on. So this is the new airport. And so observations on Asian airports, runway system capacity has become the bottleneck, massive capital investments in airports. China has a program to build 200 new airports in Western China. Okay? Amazing investment in airport infrastructure. India is beginning also to move aggressively. Southeast Asia, again, more and more runways there. Finally, and I promise I'll finish in a few minutes, observation on European airports. Well, this is a sad story. In Europe, there is no political will whatsoever to increase runway capacity. The public is against it. The politicians are also following the public signals. And there have been very, very few additions to the runway system in Europe. And what they do essentially is sweep the problem under the rug. What do we mean by that? They impose limits on how many movements can be scheduled at an airport. In other words, they do what we called before slot coordination, the level 3 airports. So sweeping the problem under the rug, heavy and increasing reliance on slot coordination amounts to increasingly regulated access to the market in Europe. And I say it's the world's most problematic region in terms of long-term ability to match capacity to demand. Just to show you what I mean, this is the number of level 3 airports in the world in summer 2017. Of the 178, 104 of these airports are in Europe because, again, they don't have some capacity, so they just say, that's it, limit here, and I'm not going to accept any more traffic. So they have placed a cap on the growth of air transportation. And just to show my last slide, remember I mentioned the grandfather slots, the slots that belong to an airline as long as they use it. So, for example, as I mentioned before, Lufthansa may have 70% of and Lufthansa and its affiliates may have 70% of the slots in Frankfurt. Well, the British decided to turn this into a market by allowing an airline to sell a slot that it has to another airline. And this is some recent experience with the prices of slots. You can see here in 2012, 4 daily pairs. By that we mean a pair is an arrival slot and a departure slot. You cannot, if you get an arrival slot and you don't get a departure slot, it's useless, so you need to have pairs. 4 pairs were sold for $277 million in 2012. 2015, SAS, Scandinavian, sold 2 pairs of slots at London Heathrow, a morning pair for $60 million, and an afternoon pair for $22 million. Why so much more expensive in the morning? Because in the morning there is a lot of demand of flights from the United States that fly to London and to Europe in general, so the prices of the slots in the morning are much higher than the prices of the slots in the afternoon. And I'll just finish this example, I'm sorry. Oops, I'm sorry. Yeah. 2016, Kenya Airways sold to Oman Air 1 morning pair for $75 million. Okay? Just the right to use the runway in the morning, $75 million. That's, you can buy a new airplane, new commercial airplane, A320 or a Boeing 737 for $75 million. So these slots have become extremely valuable because of the limitations on airport capacity. And my very last slide summarizes what we have said. Limited capacity of runway complexes at the busiest airports is a problem of global importance, international dimensions, critical to the future of air transportation. The capacity of a runway complex depends on many factors. Ongoing air traffic management modernization, I'm sorry, the word airports is there. Ongoing air traffic management modernization, forget the word airports, I'm sorry, will provide only limited additional runway system capacity. More runways is the only way to have a quantum jump in capacity. Different regions of the world address the problem in very different ways, and there are numerous opportunities. Unfortunately, we do not have time to go into detail, but you'll see some slides in what I'm going to post. Numerous opportunities for people like graduate students here to do some interesting research on these topics. Thank you very much, and I'm sorry for overstepping my bounds.